and how does this impact the movement. So if I have this wire here, you know, with a small cross-sectional area, and I have no a bigger one, right? Now, within this first one here, the particles are more compact. Let's agree that both of them, hey, stop jacking on the screen, no? Let's agree that both of these have the same length, because I didn't draw it to the same length, but let's agree that it has the same length, which means that they should no, well, that probably not going to work. But now that I have a bigger cross-sectional area, my atoms are more spread out. Good. And having being more spread out means that the electrons now have more ease of flowing through the conductor. So we see where that the cross-sectional area can have an impact on the rate at which the electrons are flowing through. How are you seeing that?
Yup.
So by increasing the cross-sectional area, it increases my current flow, and by increasing my current flow, it's going to decrease my resistance. And we can look at it from this standpoint. We can manipulate the formula and put it in this way, that R is equal to V upon I. So my voltage is constant, but now if I increase this, it's going to be inversely proportional to R, right? Because we know that anything that is like this, say for example, A over A proportional to 1 upon B, this thing is inversely proportional to this. So as one increase, the other decrease. So in this case, I is increasing, which means now that R is going to decrease. And we can see it from this, where I'm increasing current flow. Good. So because I'm increasing current flow, I have a less resistance taking place here. You know, and this is due to the fact that the cross-sectional area and so. So are you clear on that?
Yeah.
Anybody have any questions so far?
No, sir.
All right. Now we're going to move to talking about series circuits for those who didn't pitch in the last class, right, that we had. Now here's an example of a circuit. Good. And by now, I don't know if everybody knows, but you know, a resistor basically is a device that pretty much limits the flow of charge. Good. That is one of the primary devices that we use to, you know, decrease or increase the flow of charge in a circuit. So in our setup here, we're going to use resistors. All right. Now, when we talk about things in series, it means that, you know, they are connected in a sequential manner. So one after the other. So in this example, I have my battery first, battery source. Then afterwards, I have a resistor, right? Then I have something else here, another resistor, and it goes on. And we can see that from this example. So that is what a series circuit is. But now we want to be able to determine our total resistance when we have a series circuit. Now,
R1 plus R2 plus R3. That would I do?
Say that again for me, please.
R1 plus R2 plus R3.
Good. So RT, which is our total resistance, is going to equal to the sum of all the resistance inside of the circuit. And we're going to denote this one as R1, R2, and R3. So R1 plus R2 plus R3 is going to give me my total resistance. Good. Now let me drop in the values. I have 4 ohms here plus 5 ohms. Somebody do the maths quickly. What will be the
5, 10, 11, 15.
good? At least somebody now sleep on the maths.
Me can't add.
So that's 15 ohms is our total resistance. Now that we have this information, we can now proceed to finding other things. Good? Now they want us to find the potential difference across the 4 ohms resistor, and they also want us to find the potential difference across the 5 and the 6 ohm resistor. Now, what do you think we're going to do to be able to can find this thing?
Sir, you're at question number 2.
Yes, so we need to find, the potential difference across the 4 ohms resistor.
Subtract something.
Put it in the voltage formula.
All right, so we now need to bring into play our Ohm's equation, our Ohm's law formula. All right, so Ohm's law would state that R is equal to V upon I. Good? Now, what I'm about to do is to find, I need to find the total current in a series circuit. Now, in a series circuit, guys, current remains the same.
No, we don't want you here, so excuse.
Current remains the same, and voltage is divided. Right? This is critical to note in that in a series circuit, the current remains constant, which means it doesn't change, and the voltage is divided among the resistors or the components that are inside of the circuit. So I have the total voltage here, which is 6. Good. Just a while ago, I found the total effective resistance of the combined resistors. That would have given me 15. Let us manipulate the formula to make I the subject. So by transposition, I is equal to V upon R. Are we there?
Yeah.
Oh, V is 6.
Yes.
Is 6 and R is
And
6.
R is 50. Yeah.
Now somebody work the maths and tell me what's going on here.
2, 6 to 12. 13. Sir. 2, 6 and 12.
Then a 2.5.
Why you don't have a calculator?
Sir, 2 and 3 over 15.
I don't want that number.
You want a decimal?
Yes, miss. That's why you should have a calculator.
0.00000.
Oh.
6 divided by 15.
0.4.
0.4.
0.4.
0.4.
Good. And what's the unit here?
Ampere.
Amps. Amperes, yeah. Good. So this is the entire current that is flowing through each of these resistors. Now that I have this value, which is the 0.4 amps, I am now able to find the potential difference across my 4 ohms resistor. I would have to go back to that formula that says that V is equal to IR, and now that I know that I is 0.4, I can multiply that by the resistor value, which is 4, which would give me a voltage of what?
1.6.
1.6.
1.6 volts. Good. So now this is my voltage value, right? So if this is my voltage value, it now means that I should expect, I basically have a remainder. So 6 minus the 1.6, right? Gonna give me 4 point what? 4.4.
4.
So I have 4.4 voltage left that is going to be divided amongst the resistor 2 and resistor 3. But now I need to break it down in a sense to find out what is happening. Who is getting X, who is getting Y? 1 second. Now we need to find out what is happening across the 5 volts. So for resistor
4, 5, and 6.
resistor 2, V is equal to IR. So in this case, it is 0.4 multiplied by the 5.
Times 5.
What is that?
2.
2 volts. Now, so from this calculation now, guys, we can basically determine what our other value in terms of the voltage across the next resistor is going to be, because we expect that the voltage is divided among all the resistors, right? So now we have 2 and we have what we call, we have 1.6 already. So we use up a total of 3.6. So we use about a total of 3.6 volts. So now I now expect that whenever I calculate the one for the 6 ohms, I must get a value
2.4.
that would add back up to the total amount that was there. So for resistor 3, V is equal to IR, and we know our current, which is constant, multiplied by 6. Let's do that and see what we get.
2.4.
2.4. Now let's do a total add up to see if we did everything correctly. Yes, we did. Whenever you add the 3.6 plus the 2.4, it now brings us back to a total of 6. So we did our calculation correctly.
The voltage reach back to 6.
Voltage.
Good.
So the 4.4 composite and break it down.
So that's what took place a while ago in regards to that. Right? Now we want to talk about but you know, I should, well, yes, yeah, let me see if I can remember. I mean, I want, because typically sometimes they will ask you to you should derive the formula for total resistance in series and parallel, right? Let's see if we can do that. Now, let's draw a circuit, right? Yeah, why interfere with my screen, man? I want to mischievous, so. Huh? All right. Now, here's our voltage, total voltage. We have R1, we have R2, we have R3. Now, the question would be, derive the formula for resistors in series. So we get a question like this, and they say, all right, derive that. Now, where do you think we're going to start from?
R1.
Eh?
R1.
But what are we going to do? That's the question.